Hello everybody, this is Dr. C. Today's pre-lecture will focus on reaction mechanisms, and so it's going to put together some things we already know, particularly in what we know about the rate law. Okay, but we're going to learn some new stuff today too, which is pretty cool. So read the first bullet there. It says, and it should say often, a balanced chemical equation often does not tell us much about how the reaction really takes place. We have our reactants going to products, but the reaction might actually be more complex than that. Even a simple reaction might be more complex than that. So in most cases, the reaction is going to occur in a series of steps. Okay? All right, so we're going to have, say, step one, step two. A lot of the mechanisms we're going to look at are going to be two-step mechanisms, but it could be three, it could be four. It really depends on how complex the reaction is. And those simpler steps that add up to the reaction, we call those elementary steps. Makes sense, right? We're going to break the reaction down into simpler steps that better represent how the reaction happens. Okay, so bullet 3, elementary steps represent the progress of the overall reaction at a molecular level, truly what's going on, okay, what's reacting with what at any given moment in the reaction. And then these sequence of steps, so we're going to have step 1 and step 2, they are going to add up to what we call our reaction mechanism. Okay, so we're going to use the rate law. We're going to use a balanced equation, but then we're going to look at, well, how does that reaction really happen? And that's what we call a reaction mechanism. All right, so let's scroll down here to the next slide. So just to let you know, we've done quite a bit of this already. All right, now we're not in the laboratory. But if we were in the laboratory, we would measure the rate of a reaction. All right. Now, what we've done in class is we say, okay, experiment 1, we have concentration of A, say concentration of B, and then we measure the rate. Okay, so that would be data for our first experiment. Okay, so those would be filled in. Remember, we have a data table. And then we run a second trial. We change the concentrations, we see how the rate changes. We might run a third trial and so on. Okay? So we run a reaction, we measure the rate. Then, and we've done this part too, we formulate a rate law. So we might say after we do this reaction that rate is equal to Ka squared. Okay? So even though our reaction involved A and B as reactants, our rate law is telling us something different. Our rate law, because we have this factor of 2 there, or the exponent of 2, is telling us that, well, it looks like that A is combining with A at some point in that reaction. B is not showing up in our rate law, so that must come in a later step potentially. Who knows? But what we're going to do then is measure the rate. We're going to propose a rate law based on the experiment. We've practiced problems like this in class. And then based on the reaction, based on the rate law we determine, we are going to propose a mechanism. Okay? So make sure you see how this sequence works. This is really an experimental science, right? We're going to run reactions. We're going to measure how the rate changes when we change the concentration. Based on that data, we propose a rate law, and then we're going to use that rate law to guide us. That's going to be our guide to propose a valid mechanism. Okay? Sound difficult? It can be. It depends on how complex the reaction is. Now, for our purposes, and again, we're not in the lab in class, right? So it's kind of hard for us to go through this whole process. Okay? I could give you one problem where you take the data and you solve for the rate law, and then you use that rate law to propose a mechanism. Probably more often than not, though, is we'll kind of work backwards. We'll say, here are some mechanisms. Here are some proposed mechanisms. Tell me if they're valid, or tell me which one's valid. Okay? So there's two criteria that we need to live by, so to speak. Okay? The steps that we propose, so our simpler steps, of course they must add up to the overall reaction, right? They must add up to that reaction. If our proposed steps don't add up to the reaction, our mechanism is certainly not valid. Okay, so that's easy. Okay, we have these steps of a mechanism. They better add up right. Now, you'll notice this term rate determining step. One of the steps in the reaction, say it's a two-step mechanism, step one, let's say that's going to be slower than step two. All right? And so your reaction can only be as fast as the slowest step. Okay? So that is our rate determining step. Our slow step is where our rate law is going to come from. Okay? So once we know the experimental rate law, we're like, oh, we know what things affect the rate. That's going to be involved in the slow part of our reaction. Okay? So when we write out our mechanism, what we've identified as the slow step, the rate law that we write from that slow step better match experimental. So rate law from the rate determining step. So we're going to write a rate law. Rate is equal to k times whatever. And that better match what we determined experimentally. Okay, how do we determine experimental rate law? We collect data, we measure the rate, we change the concentration. In class, we know how to figure that out. Or I could give you in a problem, say, the rate law was experimentally determined to be this. And then the mechanism better match that. Okay? So let's just keep going here. And before we do an example, let me show something simpler maybe. And we'll just use some generic reaction. So say I have a reaction A plus B plus C goes to D plus E. Okay, so there's my overall balanced reaction. And then experimentally, I determine, so I run the experiment, and I figure out that my rate is equal to rate constant times A to the first power, B to the first. So my reaction, and this is determined from experiment, rate is dependent on concentration of A, first order, concentration of B, first order. C is not in the rate determining step. Okay, so here's our rate law. It's saying our rate is determined only by A and B. So what we're going to do then is say, well, my slow step must involve just A and B. C must not be in there yet. So this might be a mechanism that I propose. I might say step one, A, okay, where did my pen go? I knew I could never make it through a pre-lecture without something going on here. Okay, for whatever reason, my computer has really slowed down here. There we go. A plus B goes to, say, D plus F. Okay? So I'm going to say that's my slow step because I know my rate is dependent on A and B. And so I'm going to call that step that I have A with a coefficient of 1, B with a coefficient of 1. I'm going to call that my rate determining step. All right? And then my second step is going to be faster. So this F that was produced is now going to react with C to produce E. And that's going to be a fast step. So that won't show up in the rate law. Okay, so make sure you're aware of that. What's going to show up in the rate law is the rate determining step, the slowest step in the mechanism. And then you'll notice that F and F cancel out. And if you add these together, A plus B plus C goes to D plus E. So there's our first thing we have to do. Make sure our steps add up to the overall reaction. They do. And then the experimental rate law matches the rate law that I can write from the rate determining step. Because we're going to find out, and I have a slide coming up, that says for an elementary step, so one of these two steps, these are my elementary steps, I can write the rate law directly from the coefficients. Remember, we normally cannot do that, but if it's an elementary step of a mechanism, we can. So we can't write it from the balanced equation, but we can write it from an elementary step. My rate is k, and then I use the coefficients a to the first, b to the first. And that rate law written from the rate determining step matches experimental. Okay? So I hope that kind of makes sense. So this is kind of more what we would do. We would know the overall reaction, we would know the experimental rate law, and then we would say, oh, okay, well, I know the rate determining step, so I know what to put in that step, and then try to figure out what must also be happening to get the product. Now, you'll notice that this species F is formed and disappears. I have it in a later slide. That species is called an intermediate. Okay, it's formed in the middle of the reaction, but then is consumed. Okay, so let's look at maybe more of an example that you might have on a quiz or an exam. Okay, so here's a real reaction. We have nitrogen dioxide and carbon monoxide to produce nitrogen monoxide and carbon dioxide. Now, this is kind of how these problems might look. It's going to tell you, determined from experiment, here is the rate law. All right? Rather than you determining it, you're just told that this was determined from experiment. So that is the experimental rate law. Now, here's a proposed mechanism. It appears to occur in two elementary steps, step 1 and step 2. Okay? Each of which is bimolecular. Now that term bimolecular means each reaction has two reactants. Okay? If there's only one reactant, we would call it unimolecular. If there are three reactants, we'd call it termolecular. I think you have a homework problem that focuses on that. So here is the overall reaction. Here is our experimental rate law. Here is a proposed mechanism. Your job is to tell me, is that a valid mechanism? Okay? So the first thing is, do they add up? So we notice we have NO3 as a product, 1 mole. 1 mole is a reactant. That's an intermediate. Cancels out. Does anything else cancel out? Oh, 1 mole of NO2 as a product is going to cancel out with 1 mole of NO2 as a reactant. And we end up with NO2 plus CO goes to NO plus CO2. Check. So the first step in determining is a mechanism valid is, do your elementary steps add up to the overall reaction? Yes. Okay. Now, what's the next step? The rate law written from the rate determining step must match experimental. So then we're going to have to say, and so I didn't put it in here, so this slide, and this is in the notes posted in Sapling, just says, do they add up? We did that. Okay? So we've already done that. We did talk about intermediates. NO3 is formed and then it's consumed. That's called an intermediate. But then here's the next part. Does the rate law written from the rate determining step, does that match experimental? And as I've already talked about in this pre-lecture, if it's an elementary step, we can write the rate law directly from the coefficient. We can't do that for a balanced equation, but we can do it for an elementary step. So in this case, we have a coefficient 1 for A. There's our exponent in our rate law. And this reaction, as another example, okay, this reaction is actually 2A plus B going to products. All right, so we have a coefficient of 2. There's our exponent of 2. So it's second order with respect to A, first order with respect to B. Okay, and again, that's only for an elementary step. So, going back to our mechanism. Okay, does the slowest step match this experimental rate law? Okay, now, for now, we're going to leave it at, if it's the first step in the mechanism, it's really easy because we can write the rate law directly. We're going to look at a harder example in class where the slow step is further down in the order. You know, it's not the first step. But where'd my reaction go? Oh, well, I lost my reaction. I'm going to have to scroll back up here. I thought I had it written again. Okay, so let's just go, so they add up. Let's go back. So what I'm going to put here is, to make this a valid mechanism, I'm not going to make you do this. These would be labeled. But let's label the first step slow and the second step fast. Okay, based on what we know, we can write the rate law for either of these two steps from the coefficients, since they're elementary steps. So for this first one, I can write rate is equal to K NO2 squared, because it's 2 NO2 in the first step. So this is step 1. Okay. Step 2 would be rate is equal to K NO3 to the first power, because there's a coefficient of 1, CO to the first power. Now, this one is labeled as our fast step. It's not going to be our rate determining step, so this will not match experimental. The slow step, which we're calling the first step, if it's a valid mechanism, the rate law written from that slow step must match experimental. Does it? Yes. Okay? So this might seem to be a little convoluted because we're really working backwards. Okay, just to remind you to wrap this up. Normally, we're going to run an experiment. We're going to measure the rate as we change the concentration. From our rate and concentration data, we then propose a rate law, an experimental rate law. Once we know that rate law, that's going to guide us to propose a mechanism. Okay? In these problems, we're in effect going to work backwards. We're going to say, here's the experimental rate law. Here's a proposed mechanism. Is it valid? What do we look for? Do the steps add up? Do the elementary steps add up to the overall reaction? Check. Does the rate law written from the rate determining step, the slow step, does that rate law, and I'm drawing everywhere on this screen, does that rate law written directly from the slow elementary step, the rate determining step, match experimental? In this case, check. What do we say? It's a valid mechanism. Okay? We will practice one of these in class. There's one of these in the pre-lecture quiz. There are some simple ones, just how do you write a rate law from an elementary step. But then we'll also look at a more complex one where the slow step is not the first step in the mechanism. And we're going to have to do a little bit more work to figure out what the rate law from that slow step is. We just can't technically write it directly, and I'll explain why in class. Okay? So, there you go, reaction mechanisms. I will see you in class on Friday.